All right, we're going to talk about the gradient in spherical coordinates. So from the homework or from previous classes, you may know that the gradient is written grad f, the gradient of a function f. And in Cartesian coordinates, we can write it as partial f partial x times the vector x hat plus partial f partial y times the vector y hat plus partial f partial z times the vector z hat. And so that if I take x hat dotted with grad f, what I get is df dx x hat dotted with x hat plus df dy x hat dotted with y hat plus df dz x hat dotted with z hat. And because the x, y, and z are orthogonal coordinates, the unit vectors are all orthonormal, so x hat dot x hat is just 1. X hat dot y hat will be 0, right? X hat and y hat are perpendicular vectors, so their dot product is 0. And same thing over here, x hat and z hat is 0. So if I take, what I find is that by taking the unit vector in the x direction and dotting that with grad f, what I get is df dx. Right, so I get the x component of the gradient just by dotting with x hat. And similarly, if I was to do y hat dotted with grad f, I'd get the y component of the gradient vector. And this is we're going to use this property to try to find out what the coordinates are of grad f or what the components are of grad f are in spherical coordinates. So namely, I'm going to compute these quantities here. R hat dotted with grad f, phi hat dotted with grad f, and lambda hat dotted with grad f, where r hat, phi hat, and lambda hat are the unit vectors in the r, phi, and lambda direction. If I write down a Cartesian axis with z, x, and y, and some point here a, and I call this vector RA, and I pick another point out here, and I call this point B, and the vector connecting them RB, and then another one out here, C, and another one out here, D. So what have I done? So the RA here, RA is R cos phi cos lambda, R sine phi, no, cos phi sine lambda, and R sine phi. And then the vector B will be one where I just perturb it in the R in the radial direction. So RB will be R plus delta R cos phi cos lambda, R plus delta R cos phi sine lambda, and R plus delta R sine phi. The point C, RC, will just be the one where I perturb the phi coordinate. So this will be R cos phi plus delta phi cos lambda, R cos phi plus delta phi sine lambda, and R sine phi plus delta phi. And finally, the point D, I will perturb lambda. So RD will be R cos phi sine lambda plus delta lambda, not sine, cosine here, R cos phi sine lambda plus delta lambda, and R sine phi. And so these vectors are changing in the direction of this one is in increasing phi, this one increasing r, and this one from a to d in the direction of increasing lambda. Let's do the r direction. So if I do delta r is equal to rb minus ra, that's going to be the difference between these two vectors, right? And that's just going to be delta r times cos phi cos lambda cos phi sine lambda sine phi. And so if I want to make delta r, if I want to make a unit vector in that direction, namely r hat, what I would do is I would take delta r and divide it by its length, which is just delta r in this case, right? Remember that if I square and sum the components of dr and then take the square root, all I'll be left with is delta r. So that's the length down here. So delta r is equal to just delta r, the magnitude of it. So this is the unit vector in r hat direction. And if I take r hat and I dot it with, no, if I take, sorry, delta r and I dot it with grad f, right? What I should get, since the increment is a small increment, I should just get f at rb minus f at ra. Right, that's the property of the gradient, is that if you take, for small increments, if you take the dot product of that delta r with grad f, you just get the difference of the value of the function. And that will just give me f at r plus delta r phi and lambda minus f at r phi and lambda. And so now if I divide both sides by delta r, right, I divide by delta r, divide this by delta r, then this looks a lot like r hat, or it is exactly r hat dotted with grad f, right? And on this side, if I take the limit that delta r goes to 0, this is just the FDR. And this, remember, is just equal to r hat. So this is also equal to r hat dotted with grad f. And therefore, r hat dotted with grad f is just dfdr. And so this is df dr, which is the r component of the gradient. So it looks a lot like a Cartesian expression, right? You just take the partial derivative with respect to the coordinate. But it'll be slightly different for these two. So let's now do the phi hat direction. So now if I do RC minus RA, that will be the difference between this minus that, and what I'll be left with will be R, and I'll open a parenthesis, cosine of phi plus d phi minus cosine phi, close my square bracket, cosine of lambda, R cosine of phi plus delta phi minus cosine of phi sine of lambda, and the last one r sine of phi plus delta phi minus sine of phi. That's that. So now if I take the magnitude of delta r, I will, let me simplify first. So this part here, cosine of phi plus delta phi minus cos phi, if I take the limit where delta phi is small, that will be equal to just minus sine phi delta phi. So this will be equal to r minus r sine phi cos lambda delta phi minus r sine phi cosine lambda delta phi, and r cosine phi delta phi. Right, so the derivative of cosine is minus sine, so I get minus sine, and here's the finite difference, but if I delta phi is small, I could just multiply by delta phi. And now if I want to get the magnitude, I will just square the components and take the square root. You can see quickly that if I square and add the first two components, the lambdas will go away, and I'll be left with just r squared sine squared phi delta squared phi, and the last one r squared cos squared delta phi squared, and so the cos and the sine will go away, and all I'll be left with is, for the magnitude, sorry, which implies that delta r, the magnitude of that is just r delta phi. So let me just just copy that over here to make some room. The magnitude of delta r in this case is just r delta phi. So that's the length of the vector when I move in the phi direction. Okay, then I can now do delta r dotted with grad f, which will be f at r of c minus f at r of a, which will be f at r phi plus delta phi and lambda minus f at r phi lambda. And then if I divide both sides by r delta phi, I will get, well, when we write it, I'll get delta r over r delta phi dotted with grad f is going to be equal to, and on this side I'll get f at r phi plus delta phi lambda minus f r phi lambda divided by r delta phi. And if I take the limit of delta phi going to 0, this will just be 1 over r df d phi. And on the left-hand side, this is just the unit vector in the phi hat direction. So this is just phi hat dotted with grad f. And so now I just found the phi component of the gradient. It's just 1 over r df d phi. Okay, now we'll do the last one in the lambda hat direction, which is going towards d. So this time, delta r is equal to r at d minus r at a is the difference between this and that. So if I take the difference, I will get r cos phi cos lambda plus delta lambda minus cos lambda. Oops. R cos phi sine of lambda plus delta lambda minus sine lambda, and r sine phi. Oh, no, just 0. Sorry, the last component is just 0. And just like before, this looks like the derivative of cosine multiplied by delta lambda, and this looks like the derivative of sine multiplied by delta lambda. So what I get is r cos phi cos lambda, no, sine lambda, with a minus sign and a delta lambda. In the second term, I get r cos phi, and this looks just like cosine of lambda times delta lambda. The last term is 0. And if I try to get the length of dr, I will square and sum, and I will be left with delta r, I'll write it up here. That means that the length of delta r, square and sum and take the square root, that is just r cos phi. Right, the sine squared plus cos squared goes to 1, and then with r cos phi, delta lambda, oh, delta lambda squared, delta lambda, forgot that term. Now, I will dot delta r with grad f, and that will be f at r of c minus f at r of a, and that will be equal to f at r phi lambda plus delta lambda minus f at r phi lambda. So far so good. Then I'm going to, just like before, I'm going to divide both sides by the magnitude of delta r. So delta r divided by r cos phi delta lambda dotted with grad f will be equal to 1 over r cos phi times f at r phi lambda plus delta lambda minus f at r phi lambda, all divided by delta lambda. And now if I take the limit of delta lambda going to 0, what I get is 1 over r cos phi df d lambda is equal to 1 over r cos phi df, whoops, df d lambda. And this is a unit vector, right? I divided delta r by its length, and it's a unit vector in the lambda direction, so this is just lambda hat dotted with grad f. And so therefore the component of lambda hat of f of grad f in the lambda direction, the longitude, is 1 over r cos phi df d lambda. And so this gives me the three components of the spherical coordinates. To write it out neatly, what I have is following. Grad f is equal to, as before, df dx times x hat plus df dy times y hat plus df dz times z hat. Or, using this notation, I could get df dr times r hat plus df d phi times 1 over r phi hat plus 1 over r cos phi df d lambda hat. Where now r hat, phi hat, and lambda hat are the unit vectors in spherical coordinates. Okay, so that's how you do the gradient in spherical coordinates.